Okay, so with this first example, we want to factor this. Now, it looks like it's kind of factored a little bit already because we've got those sets of parentheses. But let's first of all, let's look at the fact that all of our terms here have 2x plus 1. They have something in common. And then beyond that, if we also look at these middle two terms, they are exactly the same, 3x times 2x plus 1, except one of them has a plus in front of it and one of them has a minus in front of it. So really, right off the bat, we can cancel those two terms because they are exactly the same, but one of them is positive, one of them is the negative. So we can just throw it out. We don't even have to worry about it anymore. Past that, now we want to examine these two terms and compare them to each other. We do not want to distribute the 8x cubed because our goal here is we're trying to factor. We don't want to multiply because that's going in the wrong direction from factoring. Factoring is the opposite of multiplying, so we don't want to go down the multiplying road. We want to keep going in the factoring. So we're not used to looking at a common factor that's a binomial, but that's what these two terms have in common. They both have 2x plus 1, so that is our GCF here. So if we pull that out in front, we are left with the 8x cubed from the first term. We pulled out the 2x plus 1, we're left with the 8x cubed. And then in the last term, 2x plus 1 is the GCF. We don't just leave it blank. Remember, if you factor out the entire term, you've got to put a plus 1 there to hold its place. Now, you can always check your factoring by multiplying out. So look at it really quickly. If we look at 2x plus 1 as the GCF, if we distribute that, 2x plus 1 times 8x cubed, that gives us the first term. 2x plus 1 times 1, that gives us our last term. So I highly encourage you when you're factoring something, especially when it looks a little weird, every step of factoring, just do a quick multiplication and make sure that you get what showed up in the original or in the line right above that. Now, we do have one more step of factoring here because 8x cubed plus 1 is perfect cubes, the sum of perfect cubes. We looked at that briefly yesterday in the warm-up. So let's break that down. The cube root of 8 is 2. The cube root of x cubed is x. The cube root of 1 is 1. And then we square the 2x, so that's 4x squared. We multiply the 2x times 1, so that's 2x. And then we square the 1. Then we go back and assign our signs. We don't do it from the very beginning. We wait until the end. We use SOAP. So the same sign that we started with, so a positive, opposite, so it's negative, and then the last one is always positive. Now, if you recall, this trinomial right here looks like it's factorable. It's very, very close to factorable, but it will never be factorable. Okay? If you have gotten it from factoring the sum or difference of perfect cubes, that is as far as that will ever factor. There is one more thing that we need to do with our problem here, though. We have 2x plus 1 and 2x plus 1. If we're writing this as our final answer, we want to shorten that, and we want to express that as 2x plus 1 squared. Now, we're not doing it to multiply it out. We're just doing it to condense the expression in our final answer. As long as it's exactly the same, you want to simplify it like that. Okay? So, a lot of little details in that problem, but very important arithmetic ideas there. Okay, let's look at B. B is a little less intimidating to look at. 15x cubed plus 18x squared plus 20x plus 24. The dead giveaway with B is that there are 4 terms. 90% of the time, if you are, no, I'm going to say more like 95% of the time, if you're given a problem to factor and it has 4 terms, then you are going to be factoring by grouping. It is always going to be factoring by grouping, or it's not going to be factorable. So we group the first two terms together, we group the last two terms together. We examine the first two terms for their GCF. So 15 and 18, their greatest common factor would be 3. One of them is x cubed, one of them is x squared, so the GCF is x squared. When we factor that out, we are left with 5x plus 6. Again, absolutely no reason not to do a quick check of your math. 3x squared times 5x is 15x cubed. 3x squared times 6 is 18x squared. Examine the second two terms for GCF of 4. When we factor out the 4, we've got 5x plus 6. If it is truly factoring by grouping, your linear factor should always be identical. Okay, that should always be identical, or else it's not really factoring by grouping. Now, you may or may not have ever truly been explained why factoring by grouping works the way that it works, and this goes directly back to the example we just did. Both terms here had the 2x plus 1, so that was our greatest common factor. That's what we're looking at right here. Both terms have 5x plus 6, so that is our common factor. So that's why typically I always write it like this. Now, usually on an answer key, the quadratic factor comes first. But I like to write it with the 5x plus 6 first because I think that truly points out the fact of why the 5x plus 6 is not squared in your final answer. Okay, yes, it shows up twice in this step, but it only shows up once in the final answer because it was the common factor. Okay, it was not squared, it's not times 2, it was the common factor, so it just goes in front. You do always want to check your quadratic term and make sure that that is not the difference of perfect squares. This is definitely not the difference of perfect squares because we don't have a difference. So you're finished at that point with your factoring. And you can do a quick check. Multiply back out. 5x times 3x squared, 15x cubed. 5x times 4, 20x. 6 times 3x squared, 18x squared. 6 times 4, 24. I got all the terms from the original problem. So absolutely no reason to miss your factoring problems there if you take the time to multiply them back out. All right, another one, 56n cubed plus 24n squared minus 35n minus 15. 4 terms, so it's grouping. 56 and 24 have a common factor of 8 n squared. So that's 7n plus 3. Just a little tip. I don't know if it'll come up later or not. I'll go ahead and mention it now. You always want to look at what you have left when you factor and check and make sure that those numbers don't have a common factor. That's one way, that's the best way to make sure that you've got the greatest common factor. Because what if I had just factored, let's say I just factored 2. I noticed, okay, 56, 24, they're both even, so 2 is a common factor. Absolutely, it's a common factor, but it's not the greatest common factor. If I had just pulled out a 2, I would have 28 and 12 left. Well, those are both even, so that means they have 2 in common. It means I didn't get the greatest common factor. So never hurts to do that little check to make sure you got the GCF. All right, second pair, 35 and 15, they have a factor of 5 in common, but here's the detail you cannot miss. That 35 was negative, so you've got to take a negative 5 out. If you don't take out the negative 5, then your signs in your linear function are not going to be correct, and it's not going to be exactly the same as the first one, and your factoring by grouping is not going to work correctly. Okay, so we pull out the factor that they had in common, the 7n plus 3. We're left with the 8n squared minus 5. Check it for difference of perfect squares. It is different, but 8 and 5 are not perfect squares. So we are finished. Haven't really mentioned this up to this point, but you do always want to do a quick check at the beginning and make sure that the entire problem doesn't have a common factor. Still not going to come up in this problem. It's close. 9, 12, and 15 are all factors of 3, but the 20 throws it off. So this one does not have a GCF for the entire polynomial. So we can go ahead and go to grouping. 3n squared. Excuse me. GCF for the first two. So we've got 3n plus 4. Second pair, -5. We had that negative in front of the 15 again, so we've got to pull out the negative. And that makes our signs work out the way that they should. So we've got the exact same linear factor, 3n plus 4. And we are left with 3n squared minus 5. No difference of perfect squares still. I think I finally have one on this next one. One more grouping example. Now, sometimes when you look at your pair, numerically, they don't have a GCF. 8 and 3 have no common factor. That's okay. They don't have to. Most of the time they do, but not all the time. But they do have a common factor when it comes to the variable of x squared. So pull out that x squared. X squared times 8x is 8x cubed. X squared times 3 is 3x squared. When we look at the second pair, you're probably thinking, well, they don't have anything in common. 8 and 3 don't have a common factor. True. The 8 has an x, the 3 doesn't have an x, so we can't do anything with the variable. True. But that 8 is negative. Anytime the leading term is negative, you've got to pull out at least, if there's nothing else in common, you've got to pull out a -1. And normally I wouldn't write the 1 there, I would just put the negative, but because of what we're doing here with factoring by grouping, I think it helps to see the -1, because here is finally an example where we do have the difference of perfect squares. X squared minus 1 is the difference of perfect squares, so this one will factor one step further into x plus 1 times x minus 1. So this is fully factored. Any questions about grouping? Okay, let's look at a few examples with perfect cubes. We did one at the beginning, we did one yesterday. I just want to make sure that we remember that process. Always, always, always check for a GCF first. 8 and 27 do not have a GCF. 8 and 27 are perfect cubes, so we can go ahead and start our perfect cube process. 2 cubed is 8, 3 cubed is 27. We square the 2 in, so square the 2 and the n. Multiply the 2n times the 3, so we get 6n, and then square the 3. So, same, opposite, always positive. And unless you missed a GCF at the beginning, there will only ever be one step to factoring perfect cubes. There is no factoring you can do past that point. That's it. Okay, example G here. 9x to the fourth minus 72x. 9 and 72 are not perfect cubes, but there is a GCF here. 9 is a factor of 72, and both terms have an x. So we want to begin by pulling out the GCF of 9x. So we are left with x cubed minus 8, which has now put us in the position where x cubed minus 8 is the difference of perfect cubes. So keep that GCF in front. It does not disappear. You got to keep it there. We've got x and we have 2. Cube the x, you get x cubed. Cube the 2, you get 8. Now we square the x. We multiply the x times the 2, and then we square the 2. So same, opposite, always positive. So this one's a negative plus plus. Those signs are very important. We are going to, our next step with this is eventually we're going to look at solving polynomials, which is the whole point of learning all these factoring methods. And if we are solving this, we're trying to find the value of x. If you've got these signs backwards, it's going to change your answer. So it's very important that you get those signs in the correct place.